Hi everyone, it's my pleasure today to introduce you to what Guochao Jason Sun. He comes from CIERA, he's a CIERA fellow. Before that he was at Caltech with Jamie Bott doing his PhD, and before that he was at UCLA doing his undergrad, so he's been in the US for a while. And today he's going to talk about hierarchical galaxies and what can we learn from them. So, first.
Cool, yeah, thanks a lot, Marta, for the introduction, and thanks everyone for coming. So it's my great pleasure to visit CITA and Canada for the first time and discuss with you some science that I'm excited about. So today I'd like to introduce some recent works from me and my collaborators whose names are listed here on unveiling the physics of galaxy formation and its large-scale effects at cosmic dawn. So to get started, here's a super not-to-scale illustration of our cosmic history, starting from the Big Bang on the left, all the way to the present day on the right, where all of our observations are made. And the particular focus is put on the so-called cosmic dawn era, which I'll broadly define here to be roughly a redshift between 6 and 30. Corresponding to the majority of the first billion years of cosmic time. And as you can see, this is the era when the first luminous objects formed, namely the first stars and the first galaxies. And also during this time, the light emitted from those first luminous objects, early galaxies, built up an energetic UV radiation background that gradually ionized the neutral hydrogen formed after recombination, permeating the intergalactic space. And we know that this is this kind of phase transition is the so-called cosmic ionization, which is generally believed to be driven by the formation of the first galaxies, which release off a background of energetic UV photons that reionize our entire universe. So centered around this so-called cosmic dawn era, here are the two topics that I hope to cover today. So in the first part, I will talk about some physics and implications of the bursty early phase of galaxy formation at cosmic dawn. And in the second part, I will use two case studies to tell you about how to study early galaxy formation collectively by probing their large effect using the so-called cosmic background radiations. So before jumping to these topics, let's first talk about some big pictures and motivations. In particular, what makes it challenging but also rewarding at the same time to study galaxies at cosmic dawn. So obviously, there are many reasons that make the studies of first galaxies very challenging, very hard. So first of all, they are prohibitively distant, very small and very faint to be definitively detected individually. So there are also sources of absorption that further attenuate the already faint light from these objects. For example, dust and the neutral intergalactic medium. In the meantime, to be sure that we're truly seeing the signal from these high redshift galaxies of interest, contaminations due to lower redshift interlopers and foregrounds, those kind of contaminations must be cleaned or at least very well controlled. And last but not least, playing with small number statistics, which is often the case for studying those extremely distant galaxies, means that there could be non-trivial sample variance and also systematic effects such as selection bias. So given all these obstacles, why should we still care? And it is basically because there's a huge gain if we can study those galaxies from the early time. We can study the growth of the cosmic structures traced by those galaxies from their ultimate origin. We can access a unique laboratory to test and to study galaxy formation theory that is mainly built on our understanding of the universe from much more recent times. And we can rely on our knowledge about these early galaxies to probe and understand what happened during cosmic ionization and beyond. And finally, we can use these galaxies to perform a variety of stress tests for cosmology and also fundamental physics. So with all these challenges and opportunities in mind, let's get started with part one for a zoom-in view of galaxy formation at cosmic dawn. And just to expand a little bit on why cosmic dawn has recently become a really exciting frontier for understanding galaxy formation, it should not be surprising to you that this has something to do with JWST, which since its launch almost 3 years ago has completely revolutionized our understanding of the high Z universe. So it has become a real game changer for hunting the first galaxies, now pushing the frontier of the earliest spectroscopically confirmed galaxies out to redshift beyond 14, as you can see from the this beautiful Lyman break here. It has identified new populations of galaxies, such as the little red dots, whose origin and possible connection to a large, previously unknown population of high redshift faint AGNs has stirred up a lot of curiosity. It has allowed a detailed chemical abundances of galaxies now to be measured out to redshift 10 and beyond, probing the earliest epochs of chemical enrichment. And thanks to the unparalleled resolving power enabled by the large aperture of JWST, especially when there's help from gravitational lensing, it has started to reveal an incredible amount of details about substructures of those early galaxies and provide direct evidence for the highly clumpy morphology of galaxies at cosmic dawn. And in addition to these excitements, another surprise that JWST has prepared for us is the discovery of a large number of UV bright galaxies and possibly massive galaxies at cosmic dawn. So I guess you may have heard of this quote unquote tension between the observed abundance of UV bright galaxies and the prediction of simple galaxy formation models assume a time constant star formation efficiency. So what I'm showing you here is some comparisons between the conservative lower limits based on observed galaxies with spec-Z conformation and the predictions of a range of galaxy formation models, assuming making simple assumptions for the star formation efficiency. And we see that these kind of simple galaxy formation models tend to underpredict both the UV luminosity function on the left and also the total amount of star formation that is measured by the UV luminosity density, which is the integral, basically the integral of the UV luminosity function. And this kind of tension is particularly strong if we look at redshift beyond 10. So it seems likely that there is something missing, or at least not fully figured out, in our baseline models of high redshift galaxy formation, which has something, and some people may even speculated that there could be some new lessons to be learned about fundamental physics and beyond our standard cosmological model. And trying to understand what's going on here is the aspect of high redshift galaxy formation that I'll further expand on for the rest of this part. So very much like other types of tensions that we have in astrophysics, many possible explanations have been proposed by approaching this puzzle from different angles. So as two examples, the plot on the top right here shows how an enhanced star formation efficiency due to inefficient feedback in those early times can result in more star formation per unit baryonic mass available, and therefore resolve this problem. Whereas the plot in the bottom right shows that the discrepancy can be reduced or alleviated if the UV light production per unit stellar mass can be boosted by having a more top-heavy initial mass function for the stellar population. While both of these kind of explanations, among several others, have clear physical motivations, they require some sort of modifications, or if you want, fine-tuning of the baseline theoretical expectations. So you may wonder if there exists an explanation that in some ways more natural. So it turns out that the burstiness of star formation in those early galaxies provides another plausible explanation for this quote-unquote galaxy overabundance problem. So the connection between bursty star formation histories and the observed number density distribution of galaxies can be actually quite straightforward. So as I illustrated here, a bursty star formation history, which is marked by strong fluctuations, strong time variations of the star formation rate of the galaxies, can actually introduce a strong variability of the UV luminosity of the galaxy, which is dominated by young massive stars. The UV variability then broadens the distribution of the light to mass ratio of those galaxies, which in turn elevates the bright end of the UV luminosity function that I showed in the bottom. And this is because the shape of the UV luminosity function decreases steeply towards higher luminosities, basically as a result of hierarchical structure formation. So there will be many more faint galaxies being upscattered than bright galaxies being downscattered when there's a large scatter present. So the net effect of the strong UV variability is basically to flatten the bright end of the UV luminosity function. This is also sometimes called Eddington bias. So in terms of the total UV luminosity density, which is, like I mentioned, the integral of the UV luminosity function, as shown in this right plot, increasing the UV variability turns out to boost the overall normalization and making it in better agreement with the observations. And as you can tell from this long list of recent literature, this whole business of bursty star formation has attracted a lot of attention lately due to the many profound observational implications it can have. So what makes this bursty star formation interpretation probably more natural when compared to the others? This is because a bursty phase of early galaxy formation stems from and is naturally predicted by a general picture of what I call galactic phase transitions here, which has emerged from state-of-the-art numerical simulations of galaxy formation, like the fire simulations. So to see what this means, here on the left, I'm showing you some star formation histories of a few galaxies from the Fire 2 simulations. And the three massive galaxies on the top, for those three galaxies, you can see a clear transition from a bursty to steady star formation as galaxies grow massive enough and develop a deep and concentrated enough gravitational potential. And so this kind of like development of like a deep and concentrated gravitational potential can help galaxies to stabilize themselves against disruptions due to, for example, stellar feedback. And you can see this is not the case for the two lower mass galaxies shown in the bottom, whose star formation histories remain highly bursty all the way down to redshift 0. So, and the two snapshots on the right show that this transition of star formation mode also coincide and likely physically connected to the formation of a like stable rotationally supported disk for the central galaxy, as well as the development of a hot and virialized circumgalactic medium that help regulate the inflows and outflows for the galaxies. And as I'll talk about later, this relates to an important distinction in the way we should understand and describe star formation in these very early galaxies. So to understand more exactly the implications of bursty star formation for the observed galaxy abundance at cosmic dawn, we turn to a suite of high redshift Fire 2 simulations that were introduced well before the launch of JWST. So meaning that these simulations are by no means fine-tuned to match the observations from JWST. So these high-resolution zoom-in simulations are able to explicitly resolve star formation and multi-channel stellar feedback in the multi-phase interstellar medium. And they predict star formation in high-Z galaxies to be spatially very clustered and temporally very bursty. And here I should also emphasize that these simulations assume a standard cosmology, and they predict a normal galaxy-scale star formation efficiency, which are in contrast to some of the theoretical explanations to the galaxy overabundance problem that we just saw. So by looking at the predicted UV brightness of the simulated galaxy, the first thing to realize is that bursty star formation can actually cause large fluctuations in the UV luminosity, which is something that shouldn't be surprising to you. And then this kind of like strong variability of the UV brightness can then induce strong modulations of the galaxy's observability. So here the upshot is that galaxies can flicker as their star formation rate changes. And especially for galaxies near the detection limit of a flux-limited survey, this kind of flickering can cause them to oscillate in and out of the observable regime. So from the mock JWST images, JWST near-cam images shown here, for example, galaxy Z5 M11D here from our fire simulations, we can see that the galaxies start from being photometrically dropped out at redshift about 8.5, and then as a pronounced starburst occurs around redshift 7.5, that happened, the galaxy just like very much like shine at this redshift. And then as the SFR starting to drop again, after this pronounced starburst, the galaxies will be, this galaxy will be undetectable again for this specific survey. So I think the upshot is here is that burstiness can make a galaxy that is closer and more massive to be actually more difficult to be seen compared with its progenitor, due to this like very bursty star formation history. So for the abundance of galaxies, we cannot estimate it directly from our simulations because each zoom-in region in our simulations is only about 1 cubic megaparsec. So to calculate the UV luminosity function from our cosmological zoom-in simulations, we essentially take the full distribution of the UV magnitude of these galaxies together with their with their halo masses sampled from individual galaxies in a collection of about 30 independent simulations, and convolve this full distribution with the halo mass function that we can predict from n-body simulations. So here on the left, the top panel shows the relationship between the UV magnitude and the halo mass, whereas the bottom panel shows the corresponding UV luminosity function. And in order to gauge the impact of bursty star formation, we further define two contrasting scenarios where we evaluate the UV magnitude of the galaxies differently. So as illustrated here by this cartoon, in the first scenario that we call bursty, the UV magnitude of the galaxies is calculated from the SEDs of individual star particles according to their true ages in our simulations without any modifications. Whereas in the second scenario that we call smoothed, we manually smooth the star formation history on purpose by redistributing the ages of the star particles to even out the star formation rate fluctuations over some prescribed timescale. And the good thing about this method is that this smooth case is guaranteed to reduce back to the bursty limit if we choose the smoothing kernel to be narrow enough. So from these comparisons, like between our simulation result with observations and between the two contrasting scenarios that we define for our simulations, we basically find two main things. So first of all, our simulations, without any fine-tuning, can well reproduce the observed UV luminosity function all the way up to redshift 12, where we stop our analysis because of the limited sample size. And we can see a good match between our simulation predictions with both the photo Z candidates at some kind of upper limit because of the contamination of possible like low Z interlopers. And also there's a good consistency between our predictions and the spectroscopically confirmed samples as very conservative lower limits. And the second thing to realize is that the bursty star formation turns out to play a very important role in shaping the bright end of the UV luminosity function, especially at redshift about 10, where we see this kind of like order of magnitude difference between this bursty case, which is true to our simulation, and our manually smooth cases. So together, these comparisons provide compelling evidence that a bursty star formation, as predicted by the fire simulations, can naturally explain the abundance of bright galaxies that JPST has observed so far at Cosmic Dome. So, yes, question?
Can you explain why the difference between bursty and smooth is bigger at the bright end as opposed to the dim end? You might imagine at the dim end you'd be dominated by individual bursts, whereas at the bright end you might average over some number. So why is it that the bright end is the one with more difference?
Yeah, so the key is that you're really looking at a differential like number density distribution here. So this is like basically the shape of the curve is telling you there are many more faint galaxies than the number of bright galaxies. So if you look at like a broad and Gaussian distribution and calculate the likelihood, it's much more likely for faint galaxies to be like scattered to have like a higher brightness than bright galaxy to be downscattered to have a lower brightness. So overall, the effect is like a flattening or elevation of the bright end of the luminosity function. But that's why the effect is most pronounced at the bright end. But of course, you're right that because of the upscatter of like faint galaxies, you do expect some like some drop at the faint end as well. But the effect is much less prominent if you only look at the shape of this luminosity function.
Sorry, I came in late and you might have mentioned this. So this is rest frame UV.
Yes.
And in the simulations, is there an AGN component? Is there any significant luminosity there?
No, so the Fire 2 simulation that are analyzed here, we have like deliberately leave out AGN by focusing on like relatively small halos, like halos below 10 to the 12 solar masses. And this is because we want to come up with like a controlled set of simulations that are like, doesn't contain the complexities due to AGN. But yeah, you're totally right that AGN, like a missing component, AGN component may also contribute to the UV brightness and also contribute to part of the problem that we talked about. So this is something that some people have published about, basically on like an AGN interpretation or AGN-based explanation for this problem, which also kind of makes sense, but of course, like it depends on like what you assume about the AGN population. And just to add to that, in the like newer generation of fire simulations, there are like prescriptions about like a black hole and AGN. So I think in the future, we should be able to come up with like a more comprehensive analysis, like including like both say effect of bursty star formation and the AGN. Yeah. Okay. All right. So I guess one thing you may wonder about the discussion so far is what galaxy scale integrated star formation efficiency do these simulations predict? So this is in the context of some other possible explanation that invoke like an enhanced star formation efficiency to explain the what I call the galaxy overabundance problem. So here I'm showing you the stellar mass to halo mass relation or stellar mass to halo mass ratio at the same redshift that the UV luminosity functions are shown. So we can see that despite an increasing scatter in this stellar mass to halo mass ratio, the galaxy scale integrated star formation efficiency measured by this ratio is actually remains generally low, and it's actually barely differs from that at slightly lower redshift, say at redshift 5 or 6. So there's no sign of an elevated star formation efficiency in these simulations, both in terms of the overall normalization and in terms of the slope. And this also agrees with the result from the cosmological fire simulation, Firebox HR, which uses the same Fire 2 physics as I analyzed here for the zoom-ins. But for the simulation is run for like 22 cubic co-moving megaparsec box. So we get consistent result no matter we're looking at the zoom-ins or the cosmological volume simulation. So a natural question is then, how should we understand this star formation efficiency as predicted by the fire simulations? So to answer this question, I'll move on to talk about some ideas to analytically approximate and interpret what's going on with these like early star-forming galaxies in our simulations. So a key prediction of fire simulations about early galaxies in this highly bursty phase is that the ISM, the interstellar medium, is highly dynamic and morphologically disturbed. And there's no clear boundary between the ISM and the CGM, the circumgalactic medium. So as shown by these plots, for a typical galaxy with a halo mass of like 10 to the 11 solar masses at redshift 5 and 6, we can see that the multi-phase gas is in the halo is characterized by strong and large temperature and density fluctuations. And due to strong stellar feedback, the gas doesn't really form a stable rotating disk like often assumed in analytic models of galaxy formation, even those applied to the high redshift universe. So instead, the kinematics of gas is very much dominated by velocity dispersions sourced by turbulence. On the other hand, ongoing star formation, which is marked by the green contours here, so these ongoing star formation is very much restricted to only the coated dense gas and spatially extends to large halo radii. So these features together make us wonder whether it's possible to describe the halo gas as some sort of density field of turbulent flows. And this is an analogy to the turbulent framework that people come up with to describe star formation in giant molecular clouds. But here we're just trying to see if this picture can be generalized out to the scales of the entire dark matter halo, given the features of this like gas distribution in these like very early and bursty galaxies. So to see how well the multi-phase gas may be approximated as a turbulent density field, we check and plot the probability distribution of the gas density contrast at different halo radii, as I labeled here on top. So from these two plots, we can see that while the distributions of gas at different temperatures are typically characterized by different PDFs, with hotter gas overall having lower densities, we can see that the total distribution of the gas density contrast is still well described by one single broad PDF that is roughly log normal. So this roughly log normal density contrast distribution is actually a well-known property of supersonic turbulence, where density fluctuations can randomly build up in a hierarchical process, and the width of the distribution depends on the Mach number and the turbulence driving mechanism. So the fact that the total density contrast PDF is roughly log normal over the entire halo means that in order to model the gaseous halo as some sort of turbulent density field, we can consider combining a simple parameterization of this probability density, for example, a log normal distribution with the radial profile of the mean gas density, which roughly speaking just follows the halo profile. So now, jumping from this slide to the next slide, so if I color code the density contrast PDF by the mass fraction of star-forming gas measured from the simulations, namely the mass fraction of gas particles with a star formation rate above 0, we can see that there's a clear boundary between star-forming and non-star-forming gas, which moves, and this boundary moves to higher density contrast with increasing radius, just simply following the density profile of the halo. However, we can see that the star-forming gas in these two panels is always restricted to the very densest end of this PDF distribution. So in the meantime, as labeled by this downward pointing arrow, the star-forming and non-star-forming gas is well distinguished by a simple density cut that matches the star formation criterion used in the fire simulations. So this is, of course, not surprising, but reassuring to see. So these features together suggest that for an analytic approximation for what's going on about star formation in these gas, so basically what gas can actually form stars, we may combine the density PDF with a simple density cut to determine the star-forming gas mass fraction at any given halo radii using this kind of turbulent framework. So now, by piecing together the different ingredients of analytic approximation that we have just discussed, we can try to understand the galaxy scale star formation efficiency predicted by the fire simulations. So in the context of this turbulent halo framework. So in particular, we would like to see if the amount of star formation in the simulated halos can be well approximated by these like analytic approximations. So the three panels here show the radial profiles of the mean gas density on the left, the star forming gas mass fraction in the middle, and also the star formation rate on the right. Whereas the solid curves, so basically, okay, so I forgot to mention that the circles are actually real measurement from the simulations for 16 different snapshots between redshift 5 and 6, along with their average shown by the white circles in this plot. On the other hand, the solid curves show the prediction of our analytic approximation given by the expression here, where we assume an isothermal halo profile for the gas mass profile, and then for the star forming gas mass fraction, we assume the prediction from a best fit log normal distribution to the analysis of our simulations.
Excuse
Sorry.
me, how do you, the log normal distribution you were setting earlier, who decides the width?
Yeah, so in these results, what decide the width of the PDF is actually just our measurement of the simulation. So we haven't tried to come up with a first principle prediction for, like, for example, how wide the distribution is going to be. And this is the next step we're going to add to this simple analytic prescription. So for example, we can use the halo, the velocity dispersion expected for the halo to calculate the Mach number and use the Mach number to predict how wide the log normal distribution can be. But I think
you set the width from the simulation, you also set the threshold from the simulation.
Yes, the threshold is taken to be same as what is assumed in the simulation. So the agreement here is by no means surprising. We should expect there's an agreement, but what is more important here is that we can actually use a relatively simple analytic prescription to capture the mean trend in the simulation. Yeah. So basically, so here, as shown in this right panel, the good agreement between the simulated star formation rate profile and our analytic approximation suggests that the normal star formation efficiency can be understood by the fact that even though the star formation efficiency in cold and dense gas can be as high as 100% as assumed in the fire simulations, the broad density distribution as a result of the turbulent driven gas will make the mass fraction of star forming gas actually quite small. And this is why when we average over the entire galaxy, we expect a relatively small star formation efficiency. So this not only this kind of analytic approximation not only explains the galaxy scale star formation efficiency, but it also provides a new physical perspective for how we can model the star formation activities in high redshift galaxy in high redshift galaxies using this kind of turbulence framework, and in particular without assuming an equilibrium disk to start with. Yes.
So from the title, does this describe only the bursty phase?
Yes. So basically, this simple framework is designed to describe the phase of galaxy formation when there's no stable disk that can be formed because of there are multiple reasons why the galaxies remain highly bursty in this case. For example, if we look at the dynamical timescale, the free fall timescale of these galaxies at these early times, it can be easily shorter than the typical time delay you would expect for supernova explosions. So in this regime, the free fall timescales can be less than a few million years. So you would expect there are certain episodes of star formation that are not regulated by feedback, not regulated by supernova feedback. So it can be really strong. There can be really strong bursts. And also like something I mentioned from the beginning, which is something to do with the gravitational potential of these galaxies in like a very early universe and early phase of galaxy formation. The gravitational potential is not deep enough for the galaxies to be like resistant in terms of the perturbations due to feedback and like disruptions due to some inflows of gas. So like all these mechanisms can contribute to the very bursty early phase of galaxy formation. And this like formalism is supposed to describe what's going on in this case.
James Beatty has a question online.
See online, there's a hand up.
Yes.
James, you should be able to unmute yourself.
Hello, can you hear me?
Yes.
This is really cool. I was just wondering, have you actually tested some of just the, very simple analytical relations that come with these log normal density PDF models? Like, for example, does the velocity dispersion over the sound speed in this entire region actually go like the dispersion of the logarithmic gas densities? Like, is there a linear relationship? Have you just tested this simple kind of statement?
Yeah, this is something we're working on right now, trying to actually say quantify the say the Mach number like over the entire halo and whether it align with our expectations. So this is something we're still working on. That's why this is still like work in preparation.
Okay, cool. Because yeah, these models only were ever really built on isothermal gas, so it's hard to believe that they generalize across an entire multi-phase plasma as well.
Yeah, so yeah, that's a good point. So we should definitely test that and see how reliable or like whether it's okay to actually try to generalize this like isothermal turbulent picture into multi-phase gas, basically. Yeah.
Thank you.
So to follow up just briefly, when it's not bursting, the star formation goes out. And so the overall star formation rate depends on something you might call the duty cycle, like how often is it bursting compared to when it's out. So is that at the factor 2 level? Like it's up and down, half the time it's bursting.
You mean after the like transition from like bursty to steady formation, you still expect some like duty cycle at the order of like
your cartoon of one invisible, 2 bursty, and 3 can't see it anymore. There's a certain cycle there. And presumably the star formation rate in 1 and 3 is low compared to 2. But you're not describing that with this model. You're only describing the bursting.
Oh yes, so that's right. So when I talk about this like turbulent framework, because of the really simple physical ingredient that go into this, we don't really capture the kind of scatter around this mean relation. This is why we're trying to capture the mean like star formation rate profile when averaged over here like 16 snapshot between redshift 5 and 6. So what we're trying to say here is that like we can like describe some like average profile of galaxy using this kind of like turbulent halo framework. Yeah, and in terms of the scatter around this, I think this is something we're definitely interested in adding to this prescription so that we can say something both about the mean trend and the kind of stochasticity around it.
It's quite a large scatter.
Yeah, you can see that like in each radial beam, the star formation rate can really vary a lot in this bursty phase.
So James, I think you have another question.
Yes.
Yeah, so is this scatter associated with your definition for n-crit? And how are you actually determining n-crit from your simulations? I know there's a bunch of theoretical models for n-crit, but I don't know how you actually deriving
So
them.
you mean for the analytic approximation, how we
Yes,
determine
on the previous slide, on the one slide back, you define a critical density for star formation occur. How do you define
Yeah.
this?
We just use whatever the simulation assumed. The simulation actually assumed like 10 to the 3 per cc for mcrit. And for our analytic approximation, we just take the same number.
Yeah, so Fire 2 has like different criteria for star formation. One of them is the critical density threshold. But I think Finn argues in his papers that it actually doesn't matter, that the virial parameter criteria are more important.
Mm-hmm. So actually in Fire, we also find this kind of critical density argument, or like a one single cut in terms of like the critical density. It doesn't, the exact value, well, as long as like around like this like ballpark, it doesn't really vary much. And this is why in the next generation of Fire simulation, the Fire 3 simulation, this like simple cut is actually removed. So in Fire 3, we no longer apply this like critical density for star formation. Yeah.
Okay, thanks. So is my understanding correct then? It actually comes from your subgrid recipe. That's how you determine n-crit. It's not actually any physics.
Yes.
Okay,
it is from the separate prescription. All right. So then, just to show more exactly what this star formation efficiency we expect galaxies to have, given our turbulent framework. So here I'm showing 2 comparisons for the instantaneous and the time-integrated star formation efficiency at redshift 6. And we can see that our analytic approximations given up here by the three example galaxies shown by the colored data points, they all seem to be in good agreement with measurement from observations, and they show no evidence for significantly enhanced efficiency of star formation, no matter we're looking at the instantaneous efficiency or the time-integrated efficiency. Okay, so I guess like before I wrapping up this first part, I will just spend a few more minutes to discuss an idea that will help us help me zoom out from individual galaxies and transition to the second part of my talk, focusing on the large-scale effect of high-Z galaxy formation. Although I realize I might not have enough time to cover the entire second part, so we'll see. So from what I discussed about the galaxy overabundance problem, you may already realize that both the UV variability and the higher star formation efficiency can elevate the UV luminosity function by making more galaxies bright. And therefore, these two effects are at least partially degenerate with each other. And this degeneracy is exactly what I'm showing you here by this figure from Julian Munoz et al. In like a very interesting recent paper. So by looking at only the UV luminosity function, it's actually hard to tell apart the effect of enhanced star formation efficiency from the effect of just UV variability. And the authors then propose a clever idea to distinguish these two effects by looking at another galaxy summary statistics, namely the clustering or two-point correlation function of galaxies. So the bias factor that can be measured from galaxy clustering turns out to be quite sensitive to the level of burstiness. And this is because bright galaxies, for bright galaxies that have been upscattered, substantially upscattered from like a low mass halos, those bright galaxies will typically have a pretty low like galaxy bias because the galaxy is intrinsically low mass and therefore less biased. So a strong UV variability will effectively reduce the galaxy clustering if we measure it as a function of galaxy UV magnitude. And this kind of reduction of galaxy clustering is particularly strong if you look at the bright end
So mind if I
of
just,
this. Yes.
mind if I just say, to clarify,
Yeah.
for people in the audience who don't do cosmology,
Yeah.
the bias in this context means tendency to exist at the peak of an overdensity, and unbiased, low mass unbiased galaxies would be everywhere, whereas the massive galaxies would be predominantly at the peaks of the dark matter.
Yes, exactly. Yeah, thanks for clarifying that. Yeah, so basically these results point to a promising way to break the degeneracy between star formation efficiency and UV variability. And they also make us wonder whether we can actually make use of these kind of galaxy summary statistics to say something more explicitly about the burstiness of star formation history. And this is how I decided to work with Julian on a follow-up analysis of this work to look into the prospect of constraining bursty star formation histories using galaxy summary statistics like the galaxy luminosity function and cluster. So to do that, we consider a simple semi-analytic framework to model the star formation history as a time series of star formation rate that can be specified by two components. So a slowly varying a smooth component that describes the mean star formation rate can be determined by halo abundance matching, which basically defines a star formation efficiency that relates the star formation rate, the mean star formation rate, to the mass accretion rate of dark matter halos. And we specify this star formation efficiency as a double power law with fixed slopes and a variable normalization, which is given by this equation. On the other hand, there is also a fluctuating component related to the burstiness of the star formation history. And we treat this fluctuating component as a one-dimensional Gaussian random variable that can be specified by a power spectral density. So, and for the functional form of the power spectral density, we assume it to be a broken power law, which is something you would expect from a damped random walk. And this power spectral density is specified by a normalization factor sigma and some decorrelation timescale for the SFR variability, and also a power law index alpha. So in total, we have three parameters: one for the normalization of the star formation efficiency, and three for the power spectral density for this fluctuating part of the star formation history. Okay, so then we can use this power spectral density to draw realizations of the star formation history. And as shown in this left plot, so the top and bottom rows show the correspondence between the star formation history and the power spectral density. And the left and right columns show two different PSD, two different power spectral density models, a shallow one that creates a lot of short-term burstiness or SFR fluctuations on short terms, and also there's a steep one that create a significantly less amount of star formation rate variability on short terms. So once we have the star formation histories, we can pass them to a stellar population synthesis framework to obtain the galaxy SCDs, including the emission lines. And we particularly focus on the H-alpha and UV continuum emission for the galaxies because they trace star formation rate variabilities on different timescales. So the H-alpha mainly traces star formation rate variations on a few to 10 million years because it is a recombination line from ionized regions or H2 regions ionized by young massive stars. Whereas the UV continuum emission has contribution from lower mass and therefore longer-lived stars, and therefore it traces star formation rate variations on maybe a few tens to up to 100 million years timescale. So as shown in this right plot, we see that in our model A, the H-alpha luminosity distribution for a given UV continuum luminosity is much more spread out compared with model B when there's much less short-term SFR variability. And this is basically because H-alpha and UV, they trace different star formation rate variations on very different timescales. So using this flexible framework for bursty star formation history and galaxy SEVs, we can sample the distribution of H-alpha and UV emission as star formation rate indicators, and then calculate the corresponding galaxy summary statistics. So as I mentioned, we're focusing on the 1-point statistics, which is the galaxy luminosity function, and the 2-point statistic, which is the galaxy clustering. So here on the left, I'm showing you the response of these galaxy summary statistics to each of the 4 model parameters we have. So one for the, as I mentioned, one for the star formation efficiency, and the other 3 for the power spectral density. And in each plot, we show the 4 different galaxy summary statistics we have, at the 1-point, the 2-point, and for UV and H-alpha. So one thing we can quickly get by eyeballing this color-coded curve is that the H-alpha is particularly sensitive to parameters that affect the temporal correlation of burstiness, namely the parameter tau decorrelation and the power law index alpha. So, so this is basically suggesting that if we want to say something about the temporal correlation of the star formation rate variability, it's good to combine star formation rate tracers sensitive to different timescales. So now we can use this framework to try to understand what kind of constraint on bursty star formation histories may be available from the observations of UV and H-alpha summary statistics. So here on the left, I'm showing you some mock observational constraints on model A in comparison to model B for a hypothetical JWST survey similar to Cosmos Web. The one thing to note here is that model A and model B are actually chosen such that they are pretty much indistinguishable if we only look at the UV statistic. So in the top row, the 2 different models can be barely distinguished. But we start to see some discernible difference when we look at this, the H-alpha statistics. And here on the right, I'm showing you some predicted parameter constraints using a Fisher matrix analysis. So, by looking at different combinations of these galaxy summary statistics shown by the different contours. So the abstract here is that the inclusion of H-alpha statistics is crucial for getting meaningful constraints on the temporal structure of the burstiness, which is captured by the parameters such as alpha and tau decorrelation. And we can also see that by the introduction of H-alpha statistics, we can start to have some distinguishing power for the 2 contrasting models whose truth values are given by the circle and the crosses here. So we, by including H-alpha, we start to be able to tell this apart. Okay, so I think this brings me to the end of the first part and probably also the end of this talk because of the time constraint we have. So just to quickly summarize, I hope I have convinced you that the early stage of galaxy formation is characterized by strong burstiness of the star formation history, which has important implications for observations such as the abundance of UV bright galaxies at this epoch. On the other hand, the phase of bursty and clumpy star formation in early galaxies can be understood and analytically described by considering the gaseous halo as a turbulent density field, which is in contrast to the often made assumption that a quasi-equilibrium rotationally supported disk exists for these very high redshift for these very high redshift galaxies. So this is a key distinction we would like to draw when we compare these simulations to what people have traditionally assumed in their analytic models. So I think with that, we can just stop here, but I think I will use 1 or 2 minutes to quickly mention what I have in the second part. So if you're interested, you can feel free to come to me and we'll talk about those larger scale effects of early galaxy formation. So in the second part, I'm basically trying to tell you something about how to use the cosmic background radiations to constrain collectively how galaxies form and evolve in early universe. So across the EM spectrum, we have all different kinds of cosmic background radiations. And also, in addition to continuum emission, we have all different emission lines. And the good thing about emission line is that we know the rest frame wavelength of this emission line, so we can actually use them to probe this three-dimensional structure in contrast to this kind of a continuum emission where we don't have redshift information, so we cannot use them to probe the three-dimensional structure. And this is the idea of intensity mapping or line intensity mapping exactly. So I think this is a familiar enough idea for people at CITA, so I don't think I need to talk about the basics. But the idea is that we can use this kind of intensity mapping technique to constrain cosmic background radiations, and therefore say something about high-redshift galaxies. So then I have like two case studies that I plan to show. So the first one is about the cross-correlation during the apocope ionization between the 21 centimeter background and the so-called near-infrared background. So the cross-correlation of the two is able to help us constrain the timeline of ionization. So I'll skip this. And of course, there are some practical challenges if we want to do like a cross-correlation like such. And in particular, in this case, when we're trying to cross-correlate a two-dimensional signal, like the near-infrared background signal, and a three-dimensional signal, like the 21 centimeter line, we have to deal with some like signal cancellation due to foreground mitigation, which causes like a mismatch in Fourier space coverage of the two signals, which will essentially cancel the direct cross-correlation signal. And we come up with a simple idea to actually first filter, like do the foreground filter for the 21 centimeter signal, and then take a square of the filtered signal before we cross-correlate it with a two-dimensional near-infrared background signal. And this is, by doing this like squaring operation, we'll actually be able to recover a non-vanishing cross-correlation signal between the two tracers and use that cross-correlation signal to trace or to time the reionization timeline. And you can see here the cross-correlation co-evolves with a stage of reionization so that we can use this to probe the reionization timeline. And this is actually a detectable signal for some like forthcoming experiment like CIERA or Euclid and also SKA lump. And so very quickly in the second case study, we return to the topic of bursty star formation, but here we're trying to constrain bursty star formation using what I show here, the C2 line intensity mapping. So the idea is that to use the C2 luminosity as a star formation rate indicator, and we can use C2 intensity mapping to trace the amount of cosmic star formation in the early epochs, and to say something about how bursty the star formation history is. So the idea basically boils down to the fact that because C2, the line luminosity traces the star formation rate pretty much like a one-to-one basis. So if we have a very bursty star formation history, we also expect these strong fluctuations in the C2 luminosity as well. So this is something we can predict using a simple analytic framework by invoking a delayed feedback injection from supernova, so that we'll basically end up with a very bursty star formation history because of this delayed supernova feedback injection. And then we can use the galaxy properties to calculate the C2 luminosity. And the idea is basically that we have a strongly mass-dependent scatter in the C2 luminosity. So when we convolve this scatter or convolve this very broad distribution of C2 luminosity as a function of halo mass and redshift, we will expect some sort of distortion in the power spectrum of the C2 intensity mapping signal. So there's a boost of the clustering power on large scales compared to the boost on there's a larger boost in the clustering signal compared to the boost in the Poisson noise term of the power spectrum. So this kind of net distortion of the power spectrum shape is could be an observable signature of bursty star formation by some forthcoming C2 intensity mapping experiment. And this is what we're trying to show here by comparing this kind of distortion with some like survey sensitivity limit. Okay, so it turns out that I can condense the second part into a few minutes, which is great. So I guess I'll just leave here my quick summary with the third point added about cosmic background radiation, and I think I'm ready to take any further questions you have. Thank you.
It was great. We're about the hours, so we need to leave the go. Any more questions online or in the room?
I wasn't sure I understand the burstiness part. So during the burst, you get 100 times more star formation rate, something like that. So the rough order magnitude?
I would say the peak to peak or the peak to trough ratio could be about 100, but or maybe a little less. It
So if
kind
I
of depends.
Right, but if I assume it's equal to same star formation rate integrated, then you should spend in the dark phase 100 times longer, shouldn't you?
So there will be some like oscillation between bursts and lulls.
Well,
I think,
so the ratio between bursty and quiescent phase should be more than 100, right?
That's something we want to know from both on the theory and on the theory level and also from observation, because the amount of time that galaxies spend in the burst phase or in the lull phase, it kind of depends on like what's going on. Like say what kind of feedback is shutting off star formation and what kind of mechanism is like rejuvenating the
Well, you know how many
gas.
stars get formed? So you take the total influence star formation to be fixed. You can't change that.
Right. That's an integral constraint you have. That's true. But
In which case, I don't understand why you say the UV luminosity function is not changed with the Big Bang.
oh,
Because there's so many stars, every galaxy that upscattered
mhm.
will be 100 galaxies downscattered.
So I guess it has something to do with the physical meaning of the luminosity function. So this is measured for like a population of galaxies. What is the luminosity distribution? So it's not for like the distribution of like one galaxy at different times. It's just at a single time, at a single redshift, what is the luminosity distribution of an ensemble of galaxies, a galaxy population. So, and because of the kind of hierarchical structure formation, we have like many more low mass halos or many more low mass galaxies than bright galaxies or massive galaxies, and that's why we expected like a very steep slope or like maybe a power law plus like a exponential drop at the bright end, or like a double power law. So that's why. Yes. Yeah.
Yeah, so I guess I wanted to ask a question about how you view experiments done with fire, because fire has to always make, it has all these subgrid prescriptions, and so any experiment you're doing is going to be within the confines of that sort of modeling space. And I guess the one that comes to mind most critically here is the assumption of a consistent initial mass function. So if you had a change in the initial mass function, I mean, you could put that into the prescription, but can you draw any conclusions about the possible variations of the IMF in these bursty phases from the experiments that you've done, given that the experiments don't have variations in the IMF, for instance?
I'm not sure I fully follow your question, but I think it has something to do with like whether the IMF that we put in or assume is fully consistent with the potential effect of variable IMF.
I'm going to posit that, for instance, perhaps the simulations will undergo the same amount of massive star formation because that's associated with feedback, and they're effectively feedback regulated star formation, and that's why, for instance, thresholds in the what is the encrypt adopted by the simulation doesn't really matter because it's a feedback regulated process.
Mm-hmm.
But the IMF determines how much low mass star formation there is going along with the massive star formation.
Yes.
So conclusions about the efficiency you get within the context of fire are
conditioned on the
conditioned on the fact that you made an assumption about how much mass there was for each unit of feedback. So is there so if you were to then try to test that after the fact, how would you go about doing it? Like Yenchen mentioned the integral constraint.
Yeah.
So there's an integral constraint in terms of mass, but that is dependent upon the IMF.
Yes.
There's an integral constraint in terms of the luminosity production, but that's less dependent upon that. And then there's an integral constraint in terms of metallicity production, which is also less dependent upon that. Can you maybe say what's the way to figure out what's the IMF and the first unit?
So my personal take is that it's really hard for us to use this kind of simulation to say something like confidently about the IMF effect because of the resolution. Basically, we don't resolve individual stars. We have no knowledge about the IMF. We have to put in something by hand, and we get what we put in. So I think the on the bright side is that like we do have some like ongoing effort on like things like by coupling this kind of simulations with something like StarForge, where we can really use like a much higher resolution simulations to simulate as close as possible from first principles, like exactly how the IMF should look like, and whether we see any variations across galaxy population or any evolution over cosmic time, and if we can sort of like combine this kind of like galaxy scale simulations with those kind of StarForge simulation using some techniques like hyper refinement or something like that.
How about observational?
Observationally, from my conversations with galaxy observers, I think I wouldn't call it a consensus, but like a common concern is that the IMF is very tricky to be observationally constrained, even in the local universe. So I guess, I mean, like, it's an interesting thing to think about. And if there's a way out, that would be super cool. But I don't know, like off the top of my head, what would be like a very unique or like distinguishing enough probe for the IMF effect, which is not degenerate with many other effects, binarity or like stellar metallicity, etc. So
to what extent in galaxies of this mass can supermassive black hole formation be associated with enhanced star formation? High mass M associates with suppressed star formation. But is the black hole at all a factor in this?
I think the short answer is we don't know yet, like because I can only tell you things about like these simulations, and we deliberately leave out black holes from these simulations.
Yeah, that's why I was asking.
Yeah. So I think it would be nice to see some like, but I mean there are other simulations that like have black hole, like Ego, like Lustrous. So I think you can
very like a top heavy IMF.
Well,
Creating a massive stars and then that leading to
the whole process of building, but just speaking as empirically as possible, the whole process of building the black hole might come with that enhanced star formation.
Yeah.
And
So
exactly the physical mechanism I'm not attempting to.
Yeah. So in some of the Fire 3 simulations, we do see that the kind of transition from like a very bursty to steady star formation is sort of like it's concurrent with a rapid buildup of the black hole mass. So once the star formation is stabilized, the black hole can grow much more efficiently. That's something people have found with Fire 3.
Yeah, so like once the potential settles and starts deepening, then your black hole grows more, maybe because everything just goes full circle.
Yes.
Yeah, we're very late. If you're interested in a further conversation, we'll be upstairs in the lounge. I think there's hot chocolate. You want some? I mean, some pastries. Or if there's in hot chocolate, that's okay. Yeah, so thank you for talking about that.
Thank you so much.
a follow-up question from what, so he was Chris Massner, the one who was asking about the replacement at the end. How confident are you that your result?